So plotting a magnetic field, how we can plot a magnetic field for a bar magnet. So example, if we have a magnet, a bar of the magnet, and we want to plot the magnetic field. So what we can use a plotting compass. What is a plotting compass? Plotting compass needle itself is a magnet. Like example, if this is a plotting compass, so 2 points are there for this plotting compass. So one end is north and another end is south. So the needle of the plotting compass itself is a magnet. So example, if we want to plot a magnetic field of a bar magnet, we have a bar magnet. So it is also having poles north and south. So what we will do, we will place first this bar magnet on the piece of paper. So example, if this is a paper, we place a bar magnet on this piece of paper. So one side is north, another one is south. Example, on the left hand side, we have a north pole, and on the right hand side, we have a south pole. And we want to plot the magnetic field of this bar magnet. So we will use a plotting compass. How we use a plotting compass? So example, I place a plotting compass at near any one. Either I can start with north or I can start with south. Example, I started from north pole. So when I place a plotting compass, so what happened? Because this needle of a plotting compass itself, one part is north, another one is south. And we know like poles, identical poles repel each other and unlike poles will attract each other. So how the plotting compass needle will point? So for explanation, I'm only using one arrow for a plotting compass. Say example, the head is representing a north of a plotting compass and the tail is representing the south of a plotting compass needle. Because the needle of this plotting compass, it is also a permanent magnet. So when I place this plotting compass close to the north pole, so south pole is attracted towards the north pole of a permanent magnet. So how the needle will point? Needle will point in this manner. So what we will do, we will mark 2 points which shows the direction in which the compass needle is pointing. Is it clear? The first part, we are plotting a magnetic field of a permanent magnet. So if we are plotting a magnetic field of a permanent magnet by using a plotting compass, so we place a magnet on the paper and place a compass. So when we place this compass, the compass needle itself is a permanent magnet, the needle of the compass. So one side is north, the example, the head is the north and the tail is the south. So when I place a plotting compass, because south pole is attracted towards north, so and north pole is repelled by the north, so a needle will point in a certain direction. The position where the needle points, we mark a dot there at that position. Then what we will do, we will move this compass, we will remove this compass and move to a new position until this compass needle shows the previous point which we marked. For example, you can see here, we move this compass from position 1 to position 2 until the compass needle is same as the direction of the previous point which we marked, and we mark another point. Then we'll repeat this procedure. We will move the compass needle we will move this compass until the needle points in the same direction as the last point which we marked. Like you can see the last point which we marked, so needle is in the same direction, and we'll mark another point. Then we'll move the compass until the needle is in line with the last point which we marked, and we have another point. And we will again move this compass needle, a compass, until the needle points as same as the last point which we marked. So we'll mark another point. So you can see we mark different points. So when I remove the compass, so what it appear when I remove the compass, I will get points only 1, 2, 3, 4, 5, 6. So when I join these points, what I will get? This line is representing a magnetic field lines which shows the direction of magnetic field. Is it clear how it is done? Plotting a magnetic field of a bar magnet. The procedure, is it clear? So if experiment is there, plan an experiment how to plot a magnetic field lines for a bar magnet. So you can do this experiment. The things which you need, you need a bar magnet, you need a plotting compass, you need a plain paper or sheet, or you also need a pencil. Now what to do, the procedure. So place a magnet in the center of the paper and draw it around it. So then place a compass near the one pole and mark dot 1 and 2. So you can see we place near one pole. This is how the compass needle. Which side is this? North or south for a compass needle? Which pole is this? Which pole for a compass needle? So it is south pole, because unlike poles attract each other. That's why this is south and this one will be north. So how it point, we mark, we have new position. Then we move the compass until the last point which we mark. So move the compass away from the magnet and position so that one of its end mark its needle by dot 2 and mark that as dot 3 and continue. So when we continue and draw this pattern, so we'll find this is how, like example, we place a compass needle at this position. So this is the first point we marked. Then we move the compass needle to new position, then another position. So we are moving the compass needle and identifying the region where the magnetic field is acting, and we'll find this type of pattern is observed. So this shows the magnetic field of a permanent magnet or a bar magnet. So you can copy this from the presentation I already shared with you. So this is a whole experiment I explained, plotting a magnetic field of a permanent magnet. So what is the meaning of induced magnetism? When one magnetic material magnetized, so when one magnetic material magnetizes the other magnetic material, this is known as induced magnetism. So what's the meaning? Like one magnetic material magnetize the other magnetic material, we call that as induced magnetism. Example, we have a permanent magnet, say steel. Steel is used to make these permanent magnets. And there are two poles of this. One is a north pole, another one is a south pole. Now, I place iron nail here and I bring this permanent magnet closer. Iron is a magnetic material, but initially it is not magnetized because there is no magnetic field. But if I bring a permanent magnet, a magnetic material, so what I will observe, I'll observe iron is attracted towards the magnet. So if iron originally it is not magnetized, but it is magnetized due to the presence of a permanent magnet, what we call this, we call that as a induced magnetism. And because of this attraction, there will be poles on this iron. So what pole will be on this side? What pole will be on the top side as it is attracted? So it will be south pole, and up down will be north pole. And this process in which we magnetize a material by the help of a permanent magnet, what we call that as a induced magnetism. Same way, if I have iron nail other side, so it is also attracted. What pole will be here? So top side it will be north, and down side it will be south. But if there is another iron nail and that is also attracted, move towards the second iron nail, what pole will be here at the top? So it will be north, and the downside will be south, and it is attracted. So when one material magnetizes the other, we call that as induced magnetism. Is it clear, the concept of induced magnetism? Yes, here the nail is magnetized by the help of a permanent magnet. And magnetic materials that are attracted by a magnet or can be magnetized, like example iron, steel, cobalt, nickel, these are magnetic materials. Non-magnetic materials which cannot be magnetized or attracted by the magnet, such as brass, copper, zinc, tin, aluminum. And magnetized material means material which act as a magnet or all have all the properties of all magnetic properties, like having magnetic pole. We call that as magnetic material. Now look, what are the effects of the current when we pass the current through So what are the effects of the current when we pass the current through a wire? The wire, when the current is passing, it is very common. Like example, if you if you are charging your mobile phone, after some time you find that the charger or the mobile, it's hot or its temperature increases. Why? Because when you are passing a current through any material or a substance, current is having a heating effect. It always produces heat. That's why electrical appliances, devices, if they are used for a longer period of a time, the effect of the heat is visible. If you are using for a short period of a time, then you don't feel that too much heat energy is evolved or change in temperature. The second effect, whenever there is a current, there is always a magnetic field. So current always produce magnetic field, because as we discussed, the magnetic field is due to the moving charges and current is due to the flow of the charges or electrons. That is why current always produce magnetic field, or we call magnetic effect of current. And there's also another effect which is called chemical effect of current. What is the meaning of chemical effect of current? Using a current, by passing a current, you can carry out chemical changes. So those who studied electrolysis, they can understand this chemical effect easily. that in electrolysis, what we do, we normally take a solution, electrolyte, and we are passing through this solution, we are passing a current through this solution. So when we are passing a current through this solution, we carry out chemical changes. So there are chemical changes like ions, movement of the ions. What we call this effect as chemical effect. Whenever the current is passing through the wire, what is the effect? Magnetic effect means there is a magnetic field around. And when current is passing through the wire, it is also having a heating effect. So it produces heat as well. So in this chapter, in this topic, we will discuss only the magnetic effect of current. Chemical effect, we will not study the chemical effect. Just as introduction, you should know that the current can also have a chemical effect, can carry out chemical changes by passing a current through a material or solution. So in this part, we will discuss the chemical effect of current. When we pass the current, in this part, we'll study the magnetic effect of current. When we pass the current, there will be a magnetic field. So three effects of current are heating, magnetic, and chemical. So we'll discuss the magnetic effect now. So what is the magnetic effect of current? When we pass the current through a wire, like example, if there is a wire, a current is passing in this direction up, or current is passing down. So what happened around the wire? There is a magnetic field. But how we can work out this magnetic field, how we can find this magnetic field? So for this, if we want to find direction of magnetic field, due to current carrying conductor. So we want to find the direction of magnetic field due to current carrying conductor. There's a rule. Which rule we use? We will use right hand grip rule. So what is a right hand grip rule? According to this right hand grip rule, your thumb, if the wire is straight, your thumb should point towards the direction of the current, and your fingers will turn around magnetic field or shows the magnetic field. So example, say you have a thin sheet, a paper, and you're passing, there's a wire in, and there's a wire which is carrying current. So wire is passing through it and it is carrying a current. This is the direction of the current. And the question is, plot the direction of or show the magnetic field around the wire. So how you will use? You will use right hand grip rule. So what is the right hand grip rule? So according to this right hand grip rule, your thumb, like example, if this is a wire which is carrying a current, your thumb should point in the direction of the current. My thumb should point up, and my fingers should rotate in a direction of the magnetic field. Magnetic field is around it. So for this diagram, for this figure, if I apply a rule, my thumb is point, because the direction of the current is up, so my thumb is pointing up, and my fingers will turn around it. So I should use my fingers to show the direction of magnetic field. So how the magnetic field will appear? So the magnetic field will appear around it. I'm using a blue shade to represent this magnetic field. The first two lines I drew closer, and the third line is relatively far. What's the reason for that? It shows that the strength of a magnetic field is decreasing. Like near the wire, it is stronger magnetic field, and away from the wire, it is weaker magnetic field. And what is the direction if I apply a right hand grip rule? So when I was applying a right hand grip rule, my thumb is pointing in the direction of the current. My fingers turned around it. So what will be the position of the magnetic field? So it will be around in this manner. Is it clear? So right hand grip rule is used to find the direction of the magnetic field due to a current carrying conductor.
Sir, it's always in this direction, the magnetic field.
It is always
It's always in this direction, the direction of the
no
hand, the
direct
direction.
direction of the current can change if the direction in the first example direct because the current is pointing up, so my thumb is pointing up. And if you
Alright.
grip this, like example, if this is a wire and there is a
Yes.
current up and I want to show the direction of a magnetic field, so my thumb should point up and fingers will turn around it because I cannot grip other way around. It's only the way naturally I can grip in this manner. So
Yes.
my fingers is showing is the direction of magnetic field is around the wire.
Alright.
Is it clear?
Yes.
So same way, and you keep this in mind that when you draw the first two field lines, it should be closer than compared to the like the distance between the first two should be smaller as compared to second and third. Reason for that, the distance between the field lines shows the strength. If they are closer, stronger magnetic field. So near the wire, we have a stronger magnetic field, and away from the wire, we have weaker magnetic field. And same way, if the current is pointing down, like if you have a wire and the current is downward or into the paper, so the same you will use the same rule, right hand grip rule again, but this time because the finger the thumb represent the direction of the current. Previously my thumb was pointing up, but now my thumb should point down. Why it should point down? Because the direction of the current is downward, so my thumb should point down, and as my fingers will rotate, it will rotate in the same as the direction of magnetic field. So the direction of the magnetic field, thumb is pointing the direction of current, fingers rotate in the direction of magnetic field. So direction of the magnetic field is around the wire in opposite direction as the previous one. So same pattern will be same, it will be circular, but the direction will be different. What will be the direction in this case compared to the previous one? So it will be opposite. Is it clear? The magnetic field due to a wire which is carrying a current.
Yes, sir.
And if we place a compass, the compass needle always point same as the direction of the magnetic field. So if I place a compass here at, say example, at point A, this was point A. So how the compass needle will point? In this manner. But if I place a compass at position B, so this is position B. So how it will point? Same as the direction of magnetic field. If I place the compass at another position C, so how it will point? Same as the direction of magnetic field. Is it clear how to work out the direction of the magnetic field due to a current carrying conductor? So you will use a right hand grip rule to show the direction of magnetic field due to a current carrying conductor. So the strength of the magnetic field depends on how much current we are passing. Like if we have, say, two wires which are carrying the current in same direction, both are carrying current. But the amount of current which is passing through the wires is different. Say example, we are here 3 ampere is passing and the other one 6 ampere is passing. So when I try to work out the direction of the magnetic field, so my thumb should point in the direction of the current and the fingers will rotate. For both, for first one or for second one, it will point, the thumb will point up and fingers will rotate around it. So when I represent the direction of the magnetic field, for both wires, the similar pattern will be there. But what about, so direction is same as we work out the direction, it is around it. But when we compare the strength, which one you think will produce a stronger magnetic field? 3 ampere, A or B? Which one will produce a stronger magnetic field?
The 6 ampere.
So 6 ampere or B will produce stronger magnetic field. So this will, so the magnitude or the strength of a magnetic field depending on how much current we are passing, and the direction of the magnetic field produced depending on what is the direction of the current. So here the similarity, they both have the same magnetic field direction, and the difference is that strength of magnetic field, this will produce a stronger magnetic field, and this will produce weaker magnetic field. And when we compare the direction is same. The direction of magnetic field, because the direction of the current is same for both wires. But this was if the wire is a straight wire. What if we have a circular wire or a coiled wire or solenoid? For circular wire or coiled or solenoid, like wire is having a loops. So we will use a right hand grip rule to find the magnetic field the same right hand grip rule. But in this case, the fingers will point or shows the direction of current, and the thumb will point towards the direction of north pole. For a circular wire, if we have a coiled or a circular wire, example, say a wire is turned around on this cylinder, the black part is representing a wire. So wire is turned around on this a piece of or a cylinder, and there is a direction of the current. Current is pointing in this manner. So if the wire is circular, how to find the direction of a magnetic field? So first thing, we have to identify or recognize the direction of So first we have to recognize or identify the direction of the current. So as you can see, like example, we have this is a solenoid, a circular wire, a looped wire. So as you can see in the figure which I drew, the current is going up. So I will use the same right hand rule, but this time for a circular wire, my fingers will point in the direction of the current and my thumb will point towards north. So as the current is going up, as you can see, the current is going up. So my fingers, as I try to grip, my fingers shows the direction of the current. So where my thumb is pointing towards left hand side. So finger shows the direction of the current and thumb is pointing towards the side where we have north. So in this example, we have north pole on the left hand side and we have south pole on the right hand side. Is it clear? So we have a circular wire. We know the direction of current. So if we grip the wire according to right hand rule, so thumb will point towards north. So if one side is north, the other side will be south. And what is the direction of the magnetic field? The orange shade is representing a magnetic field. So magnetic field is always from north to south. Around the wire, it is circular. Inside the wire, it is straight. So using a right hand grip rule, we identify the north pole. So as in this example, if we have a circular wire, so using the circular wire, we locate the north pole. So circular wire, we know the direction of the current. So thumb is pointing. If we know the direction of current, fingers rotate in the direction of the current and thumb is pointing towards the direction of north. And then the magnetic field is from north to south. Within the wire, it is straight, and around the wire, it is circular. Is it clear, this part? So it can be other way around, like you may have another direction. If this was a cylinder on which you turn the wire, wrap the wire around, so the current in this time, it's in opposite direction, it's going in this manner. And you want to find the magnetic field, or question will be like, sketch a magnetic field for this solenoid or a coiled wire or a wire turn around on a piece of iron or cylinder. So this is a wire. Current this time is in opposite direction. So my fingers will turn in the direction of the current. As you can see, my fingers are pointing in the direction of the current. Where my thumb is pointing, so my thumb is pointing towards right here. So what will be the direction of the north? So north is towards right and south is towards left. And then the direction of the magnetic field is always from north to south. Around the wire it is circular, and inside the wire it is parallel and straight lines, which is from north to south. So if I place a compass at any point, the compass needle will point as same as direction of the magnetic field. Is it clear? There's a magnetic field of a solenoid or a coiled wire, and same thing, the strength of a magnetic field depending, in this case the strength of magnetic field depends on how much current we are passing and how many loops. Like example, you can see here in this example I have how many loops? 1, 2, 3, 4, 5 and 6 loops are there. But what will happen if I increase the number of the loops? Like I have more loops. So if I increase the number of the loops, the strength of the magnetic field will also increase. So strength of magnetic field for a circular wire depends on how much current we are passing and the number of the loops of this coiled or a circular wire. So this was a straight wire. You can see for straight wire, thumb point in the direction of the current and fingers will rotate in a direction of magnetic field. The first two field lines should be closer as compared to the second and third and fourth, because the strength is decreasing. And using a right hand grip rule, you can see if the current is pointing up, the magnetic field will be around it. The finger shows the magnetic field and the compass needle will point in the same manner. So we use right hand grip rule. You can see the thumb is pointing in the direction of the current and the fingers will rotate in a direction of magnetic field. But if it is a circular wire or a solenoid, so for a solenoid, you can see here, this is the direction of the current. So if we grip the wire using a right hand grip rule, the thumb will point towards right in this example. So north is towards right and south is towards left. And the magnetic field is from north to south. So this is a right hand grip rule. The thumb is pointing towards, fingers turn in the direction of the current and thumb will point towards north. So one side we have north, another side south, and the magnetic field is from north to south. Is it clear, this topic? The magnetic field due to a current carrying conductor.